Hi, this is Sonia Doucette. In this video, I'm going to show you how to calculate the solubility of a compound when a common ion is present using Ksp. For this problem, you're asked to calculate the solubility of copper chloride in a solution of 0.30 molar sodium chloride at 25 degrees Celsius. So the first thing that you want to do here is figure out what the common ion is. And one way to do this is to write the balanced equations for the dissolution of each of these compounds in water. So for copper chloride, you'd get dissolution into the copper cation and the chloride anion. And similarly, for sodium chloride solid, you have dissolution into the sodium cation and the chloride anion. So you can easily see here, looking at all of the ions present, that chloride is the common anion. And you know that qualitatively, when there is a common ion present, according to Le Chatelier's principle, it will make the compound of interest less soluble. And this is because sodium chloride is adding extra chloride to solution. When there's extra chloride in solution, the equilibrium for copper chloride shifts from right to left. So it shifts from products to reactants because there is extra chloride present that the equilibrium for copper chloride wants to get rid of. So it will shift from right to left and form more reactant, so you'll see precipitation of some copper chloride when there is a common ion present, whether it's chloride or copper. In this case, it's chloride. So what this problem does is gives you a quantitative look at the decreased solubility of that copper chloride. So we're actually going to calculate the solubility of copper chloride given that there is a common ion present. You could also calculate the solubility of copper chloride without the common ion present, also using Ksp, and in that case you would find that copper chloride is going to be more soluble than when the sodium chloride is present. But let's calculate for this situation where we have sodium chloride present. So the first thing we're going to do is define X as moles per liter of copper chloride that dissolves in solution. Similarly, because we have a 1:1:1 molar ratio here for the reactants and the products, we also have X being equal to the concentration in moles per liter of copper, and also X is equal to the concentration in moles per liter of chloride. So we can't just take those X values, however, and substitute them into the Ksp expression and then solve for X to find the concentrations, because we have some chloride present coming from the sodium chloride solid. So the chloride concentration coming from the sodium chloride is 0.3 moles per liter. And again, you know this because of the molar ratios in the balanced equation for sodium chloride. So you're told that you have 0.30 moles per liter of sodium chloride, but for every mole of sodium chloride that dissolves, you get 1 mole of sodium and 1 mole of chloride. Therefore, the concentration of chloride is going to be the same as the concentration of the sodium chloride. So therefore, you have to consider both X and the 0.30 and say that the concentration of chloride is actually equal to 0.30 plus X moles per liter, because you have to account for the chloride coming from both the copper chloride and from the sodium chloride. So now that you know that, you can start substituting things into your Ksp expression. So the Ksp in this case, because we want to know the solubility of copper chloride, we're going to look at the products over the reactants. So the concentration of the copper cation multiplied by the concentration of the chloride anion, and again we're not including the copper chloride solid in the Ksp solubility expression because it is a pure solid. So now we can start substituting in what we know. One thing you need to do is look up the Ksp value in a table of solubility product constants at 25 degrees Celsius. And when you do that, you find that Ksp is equal to 1.7 times 10 to the negative 7. So you can substitute that into this equation. Is equal to the concentration of copper, which we know is X. We've designated it as X up here. The concentration of chloride we've determined to be 0.30 plus X. So what you want to do here is solve for X. So you have 1.7 times 10 to the negative 7 is equal to 0.30x plus x squared. And then to put that into a different form so that we can use the quadratic equation to solve for x, we want to get it in this form. So here's the general form for the quadratic equation, a review from algebra. You have ax squared plus bx plus c is equal to 0. So we want to get our equation into that form, which is pretty easy. All you have to do is move the 1.7 times 10 to the negative 7 to the other side. And when you do that, you get x squared plus 0.30x plus a negative 1.7 times 10 to the negative 7, because we've subtracted that from both sides of the equation, is equal to 0. So now you can solve for x because you know that a is equal to 1, b is equal to 0.30, and c is equal to negative 1.7 times 10 to the negative 7, because we're taking our form here and picking out the a, the b, and the c. So the way that you solve the quadratic equation is to use this format. You say that x is equal to negative b plus or minus b squared minus 4ac divided by 2a. So I could go ahead and substitute the a, the b, and the c that we have for our specific scenario into this equation, and then solve for x for two cases, for when you have the plus and when you have the minus. But that gets really complicated, and there's a lot of room for error in your math when you do that. There's an easier way to go about this, and that's going back to this part of the solution process. So what you can do at this point is try to get rid of one of the x's, because if you get rid of one of the x's, particularly the x that is going to cause you to have an x squared and going to cause you to have to use the quadratic equation, then you can more easily solve for x. So what you can do here is make an assumption, and you can assume that 0.30 plus x is equal to 0.30. And you're assuming this because you're saying, well, this x value is going to be so small that it doesn't matter. If I add that x value to 0.30, I'm still going to have 0.30 because x is such a small value, it's not going to really change this value. So in order to make that assumption, though, you have to test it. So you've made the assumption. If you assume that, then you can rewrite this equation as 1.7 times 10 to the negative 7 is equal to x times 0.30, because you've omitted this part. You're assuming that x is very small. So now you can easily solve for x, and you find that x is equal to 5.7 times 10 to the negative 7. And x is indeed a very small number. 10 to the negative 7 is a very small number. So to formally test this, just to show you, but you can already see that subtracting that from 0.3 will not make a difference. You just substitute it in to this expression. So as long as that still equals 0.30, then your assumption is okay and you don't have to mess with the quadratic equation. So you can see that this is going to give you 0.30000057. So indeed, adding the x value, which is this, to the 0.3 does not change the value of 0.30 within the significant digits that we're working with. So because in the initial problem we're given that we have copper chloride in a solution of 0.3 molar sodium chloride, we're only dealing with two significant figures, so that 5.7 times 10 to the negative 7 does not matter. So we can make that assumption. So now we've already solved for x. Here's our x. And we already know the concentration of copper. The concentration of copper is equal to x. We know that from way up in the beginning. So concentration of the copper cation is equal to 5.7 times 10 to the negative 7. And then we also said, because we have that common ion present from the sodium chloride, that the concentration of the chloride anion is equal to 0.30 plus x. And we've already seen that adding x to 0.3 does not change it, so our concentration of chloride is going to be 0.3 molar. So those are the concentrations we're trying to solve for, and we're done with our problem.